All right, guys, so let's get started. So basically, someone requested from me like some equations. So what I've done on the national project is, in addition to the video and it is this documentation, I just uploaded a sample student report. So let's see over here. So basically, it's not going to be identical because the bounding conditions are different, but the procedure and the steps should be pretty similar, no? Okay. So I'm just waiting here to open on one side. So, okay, so I'll come back once it's open. And then something else I wanted to do is about the final exam or exam 3. We say stay home. So here, be careful. I mean, work individually. All right. I don't want to see if there's an error, the same error in 10 different people, no? Okay. All right. So let's see if this uploaded already. Okay, so here you have an example. Okay, so again, in the first part, which is the final element modeling, I mean, that's not really the part that I want you to spend too much time, but this is the part that I want you a little bit, that you show me what you did, no? Define the plate elements, define the beam elements, understand what is the difference between a plate and beam element, no? The plate element represents the 3D structures, but you only represent the length, the width, and the thickness is represented outside the element, no? Okay, so you want is to a 2D element that represents a 3D. Then a line element is what? It's a 1D element that represents a 3D structure, no? Okay, so basically how you did it should be here. And then the part that you're interested is to find the maximum deformation. From the maximum deformation, you see here he finds equivalent, blah, blah, blah. So that should be kind of similar. And then the moment equations, and from the moment equation, he's able to determine the stresses. And what this guy does a bit different is actually to compare the von Mises. It doesn't compare to the normal stresses. I think it compares to the principal stresses, if I remember right here. Okay, I thought I saw principal stresses, but you have here an example, okay? So now, before we start today's lecture, this is exam 3, so let's go through it very quick to know if you have any questions. So this problem, when you look at it, determine the total deformation at point E. So basically, what do you need to do over here? You need to find what type of loads can be applied in this beam over here. Some elements are going to be subjected to axial loads and bending, no? So the total strain energy is going to contain what? In plane and bending, no? Okay. So basically you need to do all this stuff here. And does this problem look statically determined or indeterminate? What is the definition of statically determined? Correct. So in this one, basically, how many reactions are you going to have here? 3, and the static equations into D are 3. No? Okay. So this is statically determined, but again, I think I put in every single problem. Use of MATLAB is highly encouraged. I mean, I think it's crucial. If you don't do it, you're going to suffer, okay? I'm telling you right now, you're going to suffer. So let's see. What about this problem? Will it be determined or statically indeterminate? How many reactions are you going to have? How many are you going to have over here at this point? 2. In here and here. So that's 4. So that's, you only have 3 equations of equilibrium now. Statically indeterminate. And kind of the same thing. That one is going to be, that one will be different is that all these members here will just be subjected to what type of loading? Axial, no? Yeah. So you need to find using the method of joints, no? Find the axial load on each one of the members. Again, tedious. I think I put again to use MATLAB, no? I mean, this one, we have done one in class, no? The only thing that this one, I ask you also to find No, I don't even ask you to find the reactions, but we have done something similar, if not almost identical to this one. So basically, my idea is to go through the basic problem. So, wait, what happened to this one? Okay, good. So this one did not pay attention. I thought it was closed, but it's open. So what does that mean if it's open? We haven't done this problem to the truth, but what is the only difference with the procedure we have been doing? Oh, no, it's closed over here. Okay, no. So then it's good. But basically, if it's open, this would be this could be already one of the cuts, no? You can start from here to calculate the shear, no? Yeah. So this part is an open section, and this part will be a closed section, no? Okay, yeah, I didn't see that one. So okay, no, we have done something. I mean, we have done one with a member here. So if you eliminate this member, you can just solve the same problem, no? We did one that was this problem with one member here, correct? So if you put the same solution, taking this member equal to 0, should give you the solution. Fine. And removing the Q, I mean, use that one as an inspiration, as a reference. But why is that one different now here, the figure? You see? So I think it should be a line here. Maybe add it, huh? Close the cross section. I think it's from the figure I took. I didn't pay attention. Close this one over here, okay? That makes more sense to me. 500, 700. 500, 700. Okay, so we decide that it's closed, okay? It's a little bit easier. We have done this problem in class. This one, you need to do the idealization. Basically, remember the last two lectures, we found how to find the idealization, how you're going to transform this into boom areas, no? Yeah? Okay, that's basically what it is. And that's it. Okay, so I put that this, if I remember properly, I mean, do you have any question before I close the document? So I think I put on the website for this one. That the estimated time should be about 10 hours. Because the way I did this, to tell the truth, I evaluated that for me, it should take me to do this exam. To me, it would take me probably between about 4 hours. Okay, the number is not something that I do in 10 minutes, no? I'm not lying to you. I think to do the exam would probably take me about close to 4 hours, okay? So I kind of double counted twice for you because all the problems are not 100% new, but this might be a conservative value, okay? In other words, don't leave it for the night before. That's what I'm trying to say. I think it's due a week from today, correct? Yeah. So whenever is the time of the exam, I think I give you until what? Until the time of the exam? Yeah, a week from today. Is due, yeah, May 2nd at 1. All right. Okay, so do you have any question? No? Okay. So again, I'm not going to cover new material, but I'm just going to cover material that might be useful in the case you need to use it. Okay. All right, so let's go over here. Okay, so I'll put over here, this section is going to be called taper. Shear panels. Okay, so basically, if you look at the if you look at an aircraft structure, basically, I'm just saying, let's say about the fuselage and the wing. Okay, you can say that almost all panels all panels are rectangles, or at the worst case scenario, parallelogram. So basically, if you look at the panels, they are all rectangular, no? I'm sure there's some of them that are not rectangular, but I will say 99% when you look at the wing, they're all rectangular, no? When you look at the fuselage, all the panels look rectangular, or they can be, if you want, but it's still rectangular. They are parallelograms. So if that is the case, what is the sign convention that we have for shear? Remember, we had this sign convention, no? So here we have this, 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 and this. So here will be basically the same thing. All right, where all the Q's over here will be constant in all 4 edges. And that's what we have been doing all semester long, because the truth, when I look at an aircraft, I'm pretty sure some panels are not completely rectangular, but I think almost all of them are rectangular, no? Or parallelograms. I mean, parallelogram is the same, is a special rectangle, or a rectangle is a special case of the parallelogram. Okay, but the thing is, but what happens to the shear distribution when the panel is tapered? Okay, so I'm going to do kind of the derivation. I don't know until to what, how much detail, but I'll give you the concepts. I'd rather do an example. So basically, let's say we have a tapered panel. So I'm going to do the simplest case. Okay, so you see the edges are not the same. So for this one, okay, let's say that they cut over here. So I will design here a coordinate system. Y and X. So here I'm going to call this H sub L, this one H sub S. L will stand for long, S for short. Okay, that distance here will be X sub S for X sub short. This will be the length of the panel in the X direction. And this, everything here will be the X long. I'm going to define two angles. This will be theta B for bottom, and this will be theta T for top. Basically, we're going to have the S stands for short, L stands for long, B stands for bottom, and T stands for top. Okay. And the shear panels are assumed to be constant along the edges. So basically what I'm trying to say over here is just that we'll have, I will do the figure here, let's see, here, then I did 2 at the top, this. That this will be Q long, this will be Q short, this will be Q top, and this would be Q bottom. Okay, so now we're just going to do like what we always do, is to use the equations of equilibrium. So if we do summation of forces, let's first do on the x direction equal to 0. And basically we combine these 2 figures over here. We're going to get what? We're going to say, let's say Q top. So what will be the x component of the Q top? So will be Q top of L over cosine so this will be Q times the amount of the length. If you want L top, okay, would be this value over here. Now we need to take the x component, will be cosine theta t. So Q top minus Q bottom, we do something similar. That's what? L over cosine theta bottom times cosine theta bottom equal to 0. So you can see that this simplifies a lot. We're gonna have Q top times L minus Q bottom times L equal to 0. Or from here, we can find Q top equal Q bottom. Yeah, I mean, you can do this stuff because you can cancel the L. And let's just call this one, since they're equal, we're going to call this one Q hat. All right, so we're going to do something similar now. We did the summation of forces on the X. We're going to do the summation of forces on the Y. Do summation of forces on the Y equal to 0. Again, you need to keep in front of you these 2 figures, okay? All right, combine and combine them. So you do summation of forces on the Y, you're going to find minus Q sub S, as you got it, minus, so these ones are literally on the y direction, will be minus q sub s times hs plus q sub l hl Now, the other two, okay, we'll have the same thing we did before we did the x component. We need to do the y component of the top and the bottom. So this kind of similar. This will give us that plus, let's see what before, plus q top L cosine theta top. So if before was sine, this time is going to be, sorry, before was cosine, this time is going to be sine minus q bottom of L over cosine theta bottom times sine theta bottom. Okay, but remember that from the equation we just derived, what do we have? Q sub t equal q sub b equal q hat. So to simplify again, not giving too much detail on the derivation, this will be q hat q hat this is going to give us what? So let's see. Let me just rewrite it if you want. QL H sub L will be equal to Q sub S A sub S so let's see that one. So I move that one to I need to move that one to the other side. Okay, plus Q hat L tangent theta bottom minus Q hat L tangent theta top. And this is going to give us that Q sub L is Q sub S A sub S over S H sub S over S sub L. Okay, so here I'm going to change the notation. Be careful with this. Minus Q of okay, minus Q of L tangent the top minus L tangent theta bottom. This value over here is HL minus H short, H long minus H short. Okay, so to make it short, this will simplify to Q sub L equal to Q sub S H sub S over H sub L minus Q hat oops, okay, HL minus H sub S. I forgot here something. Okay. Over H sub L. Okay, this value here is actually not only equal to this, it's equal to this, okay? Okay, and finally, we do the summation of moments. About this point over here, there would be point A. I mean, this is just, we're almost done. All the division is not that important. But basically, this will give us that Q sub L, HL times L minus Q hat L over cosine theta top cosine theta top times HS equal to 0. So from here, we find that Q hat equal to QL H sub L over H sub S. All right, so you want to call this one A and B. Almost there, okay? All this part is not that important, but substituting B into A, we get QL will be equal to what? QS of HS over HL minus Q that we over here would be the QL HL over HS times HL minus H short divided by HL equal to 0. And this, after just one more line of algebra, will give you that Q long is equal to Q short HS over HL squared. Okay, so now substituting, go to the next page. Almost there, okay? A, B, C. So substituting. C into B. We get Q hat Q long equal to Q long HL over HS, where QL we know is equal to QS HS over HL squared HL over H sub S. So this is going to give us that Q hat equal to QS H sub short H sub long. Okay, so that's the main reason why I don't always cover this, just if we have some time. But basically what we have done now is what? The other thing we have done is that we have derived what? What did we have initially? Initially, we had this one over here, okay? All right, so we're going to do the same thing. So this will be QL. Now, QL is equal to what? In function of the other ones would be QL would be equal to, we did on the page before. So let's see, what is that one? Okay. This one that I haven't done, but forget about it. Basically, I want you to know that Q here long will be equal to Q short of H short over H sub L square. Going up. Now, this one will be, if you want to call it Q short, okay, everything will be in function of Q short. Then what do we have over here? Q top, okay, that one over here. So that might be Q top will be equal to QS H of S H sub L, and this is also the Q. This one. And then at the bottom, we have Q, which is Q hat equal Q bottom, will be equal to Q sub S, H sub S over H sub L. Okay, so like I was saying, I don't generally cover this because the only way for you to do these problems in order, and if you don't have to redo the whole division, is to give you this figure over here. As one equation. Yeah. Okay. So let's do a quick example. All right. Let me go to the next page. So basically, you see the difference. All right. Is that we say that if you have panels that are rectangular or the shape of a parallelogram, the Q will be constant in all four edges. Yep. Now, what happens if these four edges are tapered? They are not the same. So this one different length than this one. All right. So in this case, you will still assume that they are constant along each one of the edges, but you see one of the edges will have different value, no? That's basically what it's saying. Okay. So let's do an example here. Let me go to the next page. So over here, we have a panel. Okay, and it's not going to be to scale at all. Okay, and if you want to look at the boundary conditions, All right, doesn't matter. Let's got this 1, 3, and 4. We have a force here of but 5,000 newtons, but could be 5,000, doesn't matter. We know this length over here is 1 meter. We know this length over here to be 0.45. Okay, so the question is determine. They give more data on this function, on this problem, but I don't think we need more information. Okay, so let's say it will be panel. Determine the shear flows in the panel. Okay, so basically it's going to be hard for me to do it, but basically what I need to do is to look at these two figures, no? Yeah. Okay, so basically here Q34 should be the same as the Q short side. Okay, so let's say Q short will be equal to Q34. And what should be that value equal to? What is going to be the function of that membrane? How would you find here the Q short or the Q34? Okay, let me do here the panel again. I do here 3 and 2. So basically, we use the same notation. What are we going to over here? This will be Q short. If you want, I'm going to put this Q long will be what? Q12, Q top equal to Q bar, Q hat equal to Q14, and Q bottom equal to Q hat equal to Q23. All right, this is easy to do. That's Q top. How can we find Q short? What would be Q short? No, I mean, that's the way we did it. What member will be carrying this load? The one on this side of the panel, no? So this will be what? What was the length over here? What is the length? 0.45. So we do this, what should we have? We should have what? QS times 0.45. I guess we'll do meters. 0.45 meters. Okay, now what do we do? Minus 5,000 equal to 0. So this is going to give you what? QS equal to, I have a value here is 11,110. Yes.
Isn't QB, QB also just if we're doing a point analysis at that point?
Q, which one is it? Q, the QL here or?
QB, isn't QB also resisting the force as well?
On,
if you do a free body diagram of the point of.
Yeah, you will say, I understand what you're saying. You say they are here, okay. Yes, but, okay, let me ask a question. What are we assuming all the time? So remember, this is a panel, but each one on the side of the panel is going to be a stiffener. Okay, so we assume that the stiffeners will only carry load in one direction. There are two force members. Okay, so here you see there's no load in that direction or that direction, no? So that's a good question. So we have here Q sub S, if this is correct, equal to 11,110 newtons per meter. Okay, so now what do we need to get to do? Using these relations now, we can find out what would be the value for the other ones. Okay, so using the relations from the, let me call this one A, from the figure capital A. So let's see. We will have what? According to this, Q long will be equal to Q short H sub S over H sub L square. So this should be equal to what? 11,110. What is H sub S? 0.45, correct. And the long, we did not give it, no? Do we have a value for H long? No, I forgot to give it. So they don't give it on these figures. So I mean, we can make it up. We can make it up. That way we don't have to come up with these values here, but you don't have to do the calculations. All this stuff, so we're done. Okay, so what value you want to give for H long then? Okay. It's just for the example, okay, 0.60. So we divide that by 0.6. What do we get? I mean, let's do all of them and then you can give me the values. Then we have here QB to be equal to Q short HS over HL. I forgot to put the square over here. So this will be the 11,110 0.45 divided by 0.60. You will give me the value. And the last one we need to do is Q top. I mean, we already have it, so it should be the same thing as the Q bottom, equal to the Q hat, which should be whatever we have before. So can you give me some values over here, please? 832.5, so it will be 832.5.
Q long, 624.37.
Yeah. So basically at the end, this one, 2 over here. If we do the distribution, what we got is here. So 11,110 for Q short. Q long, we're gonna get 624.375 Q long, and then these two should be the same. $832.5 and $832.5 equal Q top equal Q bottom. Okay, so like I said before, the reason I don't really cover this in class because I think it's, I mean, in the normal problems is that I think there's already enough work by having rectangular panels that having to then redo all this stuff for no rectangular panels, no? Okay, and when I look at an aircraft, I think all the panels to me look rectangular. Okay.